So let's consider this thermal model. So we have a hot object on the left with a temperature of T2 and a cold object with a temperature of T1 on the right. Then we stick a third object in between. So what thermal processes are going to happen? What thermal processes are going to happen?
This is going to be heat flow from hot to cold.
Yes, there's going to be heat flow. And that's this heat flow going into the object, then this heat flow going out of the object. And do they necessarily equal each other? Does Q in always equal Q out?
I would say no, it doesn't.
No? Okay. Yeah, so let me try to write this down. Yeah, Q in doesn't always equal Q out because our materials can also store thermal energy. So let me write this. So Q in minus Q out times delta T should equal the energy that is stored in this material. Do you agree on this? Q in minus Q out times delta T equals the energy that is stored in the material during this period. Yeah,
Yes.
Conservation of energy. Okay, so how do we, characterize, thermal energy storage and heat transfer? There are two processes here: heat transfer and thermal energy storage. So for thermal energy storage, so we have delta E, equals mc times delta T, where m is mass, delta T is temperature change, and C is heat capacity. So this is a property of materials. So let's say, water has a high heat capacity, so it holds up a lot of, thermal energy, and air has a low heat capacity, so it holds up a low, doesn't hold up, that much thermal energy. So that's the first equation. Then for heat transfer, we have, Q equals minus K times gradient of temperature. So where Q is your heat flux, and then you have your K, which is your thermal conductivity, and we also have, our temperature gradient. So what this equation is saying is that, if we have a really hot object and a really cold object, and, then we put it together, heat is going to flow very quickly. But if we have two, objects with similar temperatures, heat is going to flow very slowly. So that's, how the term of temperature gradient works here. So if we plug these two equations into conservation of energy, you are going to get a unified equation, which is your heat conduction equation. This tells you how temperature changes with respect to time. You will see in a partial big T over partial small t equals alpha Laplacian of T. So here alpha is your thermal diffusivity. So alpha equals K over rho C, where K is thermal conductivity, rho is density, and C is heat capacity. So alpha is, kind of characterizes the competition between heat conduction and thermal storage, because the more, the more like heat you conduct, then the less energy you store. So it's kind of like two competitive processes, and alpha, characterizes the relative competition between these two processes. So a high thermal diffusivity means, heat diffuses very quickly, heat spreads very quickly, and low diffusivity means heat is retained locally. It doesn't diffuse away quickly. So with a high, thermal diffusivity, your temperature changes quickly. Then with a low diffusivity, your temperature doesn't change quickly. And for our skin, So we have additional, terms to consider. So if we just look at the two terms on the left, this is exactly the equation we were just talking about, but in a slightly different term. This is exactly the same equation. But we need to consider that our skin is perfused with blood. So blood is very good at carrying heat or taking heat away, right? So since our blood is highly, our skin is highly perfused with blood, we need to consider the heat that is transferred in or out by blood. Then we also need to consider our cells are constantly, generating heat by metabolysis. So we need to add these two terms. So, and I also have a table here that shows you the typical parameters of the skin, including thermal conductivity and thermal, diffusivity. So if we look at this table, you will see, blood and water has a K around 0.5. And this is essentially the thermal conductivity of water. Then for epidermis, when it's dry, it's about 0.2, but when it's hydrated, it becomes 0.6. Go ahead.
So the perfusion and the metabolic heat,
Yeah.
those are separate from the gradient heat because they're generating heat, they're like adding heat to the system versus the gradient.
This is how, heat spontaneously, transport. This is the first term.
Okay.
Yeah.
Gotcha.
Okay. Great. So my question here, so for the epidermis and dermis, you will see, the K is about 0.2 when it's dry, but when it's hydrated, you will see it increases to 0.6. Why does it increase? Why does thermal conductivity increase with hydration? So, being hydrated meaning, there's more water in your skin. So water is very thermally conductive. It has high thermal conductivity. Water has a thermal conductivity of 0.6. So when your skin is more hydrated, it has more water. So its thermal conductivity gets closer to water. That's why. And then if you look at hypodermis, you will see it's almost a constant about 0.19. Why does the hypodermis has a low thermal conductivity? What is in hypodermis?
The fat.
Oh yeah, it's fat. Right. So that's a great point because we need a fat to to store heat. We don't want the heat to go outside. So that's why hypodermis has a low thermal conductivity. Okay. For thermal diffusivity, there's a similar trend here. Water is about 0.15 and epidermis and dermis has a range about, has a